Hi, my name is Montana Whitehead, and today we're going to talk about action potentials. So in the first step of an action potential, neurotransmitters are released from the presynaptic neuron, and they diffuse across the synapse and bind to receptors located on the dendrites. And when they bind to these receptors, it will cause ligand-gated channels to open here and will allow calcium to enter the cell. Now this is a graded response because the more neurotransmitters that bind to these receptors, the more ligand-gated channels that will open, and it will allow for more sodium to enter the cell. So by adding sodium to the cell, it will change the membrane potential. So the resting membrane potential is normally negative 70 millivolts, and when sodium is added, it makes the membrane potential more positive inside of the cell and more negative outside of the cell. So then sodium will begin depolarizing the membrane, and it will bring the differences between the inside of the cell and the outside of the cell closer together. If enough sodium is released, the threshold of negative 55 millivolts will be reached. And when it hits negative 55 millivolts, it is an all or nothing. Like, this is happening. It's happening. Like, there's no going back now. So at threshold of negative 55 millivolts, it will cause a lot of sodium channels in the axon hillock to open, and sodium will begin flooding the axon hillock and begin completely depolarizing the membrane. And when resting membrane potential reaches positive 30 millivolts, an action potential has been created, and potassium voltage-gated channels begin to open so that potassium may leave. But potassium will leave a lot slower because the gates open way slower than sodium gates do. So at positive 30 millivolts, this will begin to happen. So this will depolarize, and it'll be like a domino effect. And then this area will depolarize, and this area will depolarize, and sodium channels will open, and so will potassium channels, so sodium can enter and potassium can exit. And this will allow the action potential to move or propagate along the axon. The action potential will then open up a voltage-gated channel that will allow calcium to enter the synaptic envelopes. And then this will cause synaptic vesicles to fuse with the plasma membrane, and the neuron then releases neurotransmitters across the synapse to a presynaptic neuron. Now this can also be shown on this graph here. So threshold is reached by sodium ions being released into the cell by ligand-gated channels. Sodium lessens the difference between the inside and outside of the cell and brings the resting membrane potential to negative 55 millivolts. So in phase 1, we have already reached negative 55 millivolts, and sodium ions are being released by ligand-gated channels and depolarizing the membranes. And when it hits positive 30 millivolts, an action potential is then created. And in phase 2, potassium channels begin to open. Voltage-gated potassium channels will then open, which will then repolarize the membrane. And then the resting membrane potential will move past 70, and it will go to negative 80 millivolts, which is then hyperpolarization. And voltage-gated, and then to bring the resting membrane potential back up to normal, which is negative 70 millivolts, the sodium and potassium pumps will begin pumping potassium back into the cell and sodium out of the cell, because it's trying to get everything back where it belongs, because potassium is supposed to be inside while sodium is outside. And so these sodium-potassium pumps will bring the resting membrane potential back to negative 70 millivolts.